I'm David Radke, a PhD candidate at the University of Waterloo. This is work done with my co-authors Kate Larson and Tim Brecht, titled The Importance of Credo in Multi-Agent Learning. This paper is a continuation of previous work that's being published at IJCAI this July. Our research has been focused on understanding how teams impact how agents learn. A team is defined as a group of agents that combine their efforts towards a shared overall goal, and the science of teamwork is typically studied in the fields of organizational psychology and biology. In AI, teams are often implemented by providing agents some shared team-based reward signal, shown to achieve good results. In our previous work, we found that teams, when defined using a shared reward, can promote cooperation among populations with different interests, achieve higher rewards, and lead to faster learning than with agents acting independently or fully cooperative agents acting as a single group. However, a limitation of ours and others' previous work is that we assumed agents on a team fully cared about the well-being of their own team. In reality, agents and people on teams may have more complex or mixed incentives. One might imagine that even the most loyal team members can have some amount of self-interest too. For example, as a hockey player, I always want my team to win the game. However, the celebration might be a little bit sweeter if I score or perform well individually. With this in mind, the goals of this work are to explore the idea that teammates may not exclusively desire their team's reward, and to understand the conditions where teammates may exercise alternative interests and still cooperate effectively. We introduce Credo, a model that defines how agents optimize their behavior. The noun credo, defined as the beliefs or aims which guide someone's actions, fits appropriately to describe our model of how agents optimize to achieve goals. Credo is defined by a vector of parameters that instantiates a new reward function for each individual agent. Credo regulates how much agents care about various groups that they belong to, either themselves, any team that they may belong to, or the entire system. Agents that only care about themselves are fully self-focused, and agents that are entirely altruistic are fully system-focused. Teams provide a middle ground where agents can be team-focused, and various combinations of Credo parameters allow agents to partially optimize for any of these goals simultaneously. In this paper, we explore the base case where agents belong to exactly one team. So agents' Credo vectors have 3 parameters to regulate how much reward they receive from themselves, their team, and the entire system. We implement a standard multi-agent reinforcement learning setup shown here. We then enrich the environment by adding teams, defined as a partition of the population of agents so that agents belong to exactly one team as a base case. Agents can then share a team reward with their defined teammates. Although not a requirement of our model of teams or Credo, in this work we define team and system rewards as all agents in those groups sharing their reward evenly, to be consistent with previous work that groups agents together. Credo is implemented on top of these functions to regulate how much agents care for each type of reward. Since these are the only modifications to our environment, we can be confident that any modifications in learned behavior stem from Credo and teams. We analyze how Credo impacts multi-agent learning in social dilemmas with active provision, defined as when cooperation carries a cost. Social dilemmas are challenging environments of considerable interest to the recent multi-agent reinforcement learning community. We choose to evaluate Credo in the iterated prisoner's dilemma, or IPD, and cleanup grid world game environments. In the IPD, agents are paired to play a single round of the prisoner's dilemma game according to this payoff matrix. we vary the cost of cooperation and the probability that an agent's counterpart is a teammate. Agents observe their counterpart's team and receive their credo-based reward after their interaction. We theoretically calculate the conditions where agents are better off choosing to cooperate as those which satisfy this inequality, dependent on costs, benefits, the probability of being paired with a teammate, and credo. In this figure, we calculate the outcome of this equation for costs of 1, 2, and 3 as each column of plots with the benefit fixed at 5, different probabilities of being paired with a teammate as each row of plots, and every credo parameter combination with a resolution of 0.02 within each plot. To first help interpret these plots, the color at this point represents when agents are 20% self-focused, 40% team-focused, and 40% system-focused. Blue represents a scenario where if agents had that specific credo defined along the 3 axes, they're better off choosing defection. Alternatively, red corresponds with scenarios where cooperation is favored in expectation. Our 2 main takeaways from this figure are that 1, agents have less incentive to cooperate as the cost increases, and 2, that any amount of selfishness incentivizes defection in 8 of 9 environments shown in these circles. In our empirical evaluation, we implement the IPD with a population of 25 deep Q-learning agents split up into 5 evenly sized teams in the same environments as the previous figure. We evaluate credo at stepwise resolutions of 0.2, and all agents follow the same credo for the duration of experiments as a base case. The color of each hexagon within the plots represents the percent of cooperation among the population given the specific credo in that environment. Experiments with 21 possible credo combinations are repeated 5 times in all 9 of these environments, for a total of 945 experiments. Once again, we find that a higher cost decreases the amount of cooperation across the majority of credos. However, we also find that agents learn a high rate of cooperation when they're fully team-focused in 5 of 9 environments, even though cooperation is only incentivized in 1. Now let's take a further look at this case when the cost is 1. Here we also observe that cooperation emerges despite some level of selfishness, and this cooperation is stronger when offset with high team focus as opposed to high system focus. The main takeaways here are that teams allow cooperation to emerge despite the theoretical incentive to defect. And this cooperation is actually more robust to some selfishness. We expand our evaluation to the cleanup domain to study how credo generalizes to more complex environments, since agents must now learn entirely cooperative policies instead of choosing an explicit cooperation action like in the IPD. Agents must learn to clean a river to help spawn apples in an adjacent orchard. Cleaning the river carries no environmental reward, while the apples offer a reward of +1. The social dilemma is that agents must learn to clean the river in order to spawn apples, although everyone would prefer others to clean the river for them. Our experiments in cleanup contain 6 partially observable proximal policy optimization, or PPO, agents split into 3 teams of 2 each. We repeat every combination of credo for 8 trials for a total of 168 total experiments. To initially understand how credo impacts behavior, we first show the fully self-focused scenario, representing the original dilemma with self-interested agents.
In this scenario, we observe that only one agent learns to clean the river. This makes only a few apples grow in the orchard, which are often quickly snatched up by the other 5 agents that have learned to free ride. This leads to pretty low mean population reward overall.
Next up, we show the other extreme where agents are fully system focused and are all optimizing for a shared cooperative reward. This fully cooperative scenario has previously been thought to achieve the highest reward in cleanup.
We initially see the agents divide the labor so that 3 agents clean the river and 3 pick apples. Shortly after, one of the apple pickers transitions to clean the river, making a 4 cleaner and 2 picker split. This collective strategy does achieve high population reward due to an abundance of apples being generated.
However, we find that even higher mean population reward is obtained when agents are fully team focused within their component teams. In this scenario, agents share their reward function with only their teammate.
Just like the fully system-focused scenario, agents first divide the labor into 3 river cleaning and 3 apple picking agents, coordinating with their teammate so that one does each role. Unlike the system-focused scenario, the purple cleaner transitions to pick apples. The 2 cleaning agents can generate enough apples to support the 4 apple pickers, so this behavior is sustained and no other cleaner has the incentive to free ride as well. We observe this 2 cleaner and 4 picker division of labor to consistently achieve the highest reward in this environment.
With the implementation of Credo, we identified these 2 main scenarios which lead to the highest mean population reward. First, somewhat counterintuitively, we find that when agents are fully system-focused and shift to become slightly selfish, the population's reward increases dramatically.
Whereas the fully system-focused agents divided into 4 cleaners and 2 apple pickers, adding slight selfishness to the agents incentivizes 2 cleaners to learn to pick apples. This achieves the 2 cleaner, 4 picker split we observed with high team-focused populations. The 80% system focus incentivizes the 2 cleaners to continue cleaning, and the environment remains stable and achieves high reward.
The second scenario is when agents have high team focus. We find that high rewards are still obtained by agents with high team focus regardless if they are a little self or system focused as well. As an example, consider this case where high team focused agents are also slightly selfish and still achieve high rewards.
This reward is achieved by the agents still collectively learning to divide labor into 2 cleaners and 4 pickers.
While mean population reward provides an indication as to the global productivity, measures of equality give context to the dispersion of the reward across a population. We examine the inverse Gini index for each Credo combination, where a value of 1 means perfect equality and 0 means one agent holds all of the wealth. We find that every combination of Credo has higher equality than the fully self-focused base case, and both scenarios which achieve high mean population reward also achieve high equality. In summary, we have shown that when placed in teams, agents learn the better long-term policy of cooperation, despite their immediate incentives to defect. In cleanup, agents coordinate to learn emergent roles and divide labor in a way that achieves the highest mean population reward. We identified 2 main scenarios which achieve the highest mean population reward. And by implementing Credo, system-focused agents in cleanup actually achieve higher rewards than when they become slightly selfish. An advantage of high team focus agents is that they learn this behavior regardless of a small amount of self or system focus mixed in. Both scenarios achieve higher rewards than the fully cooperative setting, which has previously been thought to achieve the highest mean population reward. We encourage you to read the paper for more details on this work and welcome any questions or comments that you may have.